Hello, this video is on another kind of interference known as thin film interference. Okay, let's review a little bit of background that we have covered in other physics classes or other units in this physics class. The first is reminder about wave velocity. The speed of a wave depends only on the medium, and that is true for light as well. For light, we use a material's index of refraction to calculate the speed of light in that medium, where n is this index of refraction, which is a material constant. So you like n of glass has a value, n of water has a value. And c is the speed of light in a vacuum, which is 3 times 10 to the 8th. And then v is the speed of light in that medium, whatever you're interested in. Something else that we've seen in simulations and talked about briefly before, but may not be as familiar with you, is what happens to light when it crosses the boundary between two different media. So when it goes from air to glass, or from glass back to air on the other side, or into water, there's a couple interesting things that happen to light when it crosses the boundary. The first is that the velocity of the light changes, obviously because we're in a new medium. Due to that velocity changing, the wavelength is going to change as well. Remember that wavelength has a linear relationship with velocity, so when the speed of the wave slows down, the wavelength goes down as well. When the speed of the light goes up, the wavelength is going to go up. So certainly the wavelength is going to be changing as well. The frequency of the wave does not change. The number of vibrations every second is set by the wave source. So velocity changes, wavelength changes, frequency does not change. The other thing that happens is that the wave energy actually splits every time we go through a boundary, and that's pretty critical when it comes to talking about reflection and refraction. We end up with specifically two primary waves that we care about in this class, known as the reflected wave and the transmitted wave. You would see this even in a string, like if you have two strings connected to each other, like I've sort of shown in this image, a light string and a heavy string, that knot in between them would be the boundary. And if you send a wave into that boundary, when it hits the boundary, some of the wave energy continues through into the new medium, and some of the wave energy is actually bounced back into the original medium, known as the reflected wave. And one thing that is important, sort of a nuance that's critical for this current little piece on thin film interference, is that depending on which material is faster, the wave goes faster in, sometimes that reflected wave bounces back upside down or inverted. And sometimes that reflected wave bounces back the same direction, which is upright. So the rule of thumb is if the new medium is slower than the original medium, the reflected wave is actually inverted. We have a phase shift. So in this top example, right, I have this light thin string and this really big heavy string. So the wave is faster. You can see a higher velocity here and a lower velocity here. So when we hit that lower velocity, what actually happens is the reflected wave is flipped and inverted. And there's a simulation you can play around with that, which is kind of fun to do, and I'll have that posted as well later on. However, if we have the other situation where we're in our slow medium to start, and then we hit the boundary with a faster medium, then our reflected wave is actually upright. We don't get a phase shift. So that wave bounces back to the same orientation that it was before. One more note about that, transmitted waves are always upright. So whether or not they're speeding up or slowing down, the transmitted wave is always going to be upright. Thin film interference is interference on superposition between light that is reflecting off the front surface of a thin film and light that's reflecting off the back surface. So every time light hits a surface, remember some of that light is transmitted and some of it's reflected. So, you know, each one of these things is going to have light that goes through too, but what we care about is the light that we actually see. And so when you see this thin film interference, you're seeing the light that is bouncing off of that film, whether it be like a bubble or an oil slick or something of that nature. And you're getting interference between the light that is bouncing off the front of that film and different light that is going through but bouncing back off the back. Although the two photons, A and B, started off in phase, they were from the same light source, whatever it may be, we have a combination of things that causes this interference. Thing number one is the phase shift due to the reflection that we talked about in the last slide. So depending on whether the light wave is speeding up or slowing down, it may be flipped. We may have an inversion happening on one of those reflections. And then the second thing that can impact the phase of the light is the fact that these two rays have different path lengths, right? Ray B here is just going that far, but ray A has to go further because it has to go further by the distance that it travels through the film, right? So we have a path length or L difference that occurs because one of those rays is traveling further. So the combination of those two things can cause this C, which is the combination of those two rays, to be in phase and get constructive interference, or out of phase and get destructive interference based on a whole variety of factors. So let's look at an example problem and how we could calculate whether we're going to see constructive or destructive interference in a specific scenario. The most common scenario you see on a test is something like a bubble, where we have air at the top, which is a very small index of refraction because light travels very fast through it. And then we have water, and usually bubbles are primarily made out of water. There's a little bit of soap in there too, but it's bubbles. It's mostly water. And then on the other side of that water is air, okay? So what we have here is basically fast light, and then we have slow light, and then we have fast light again. And that's going to be relevant because you got to consider what's going to happen with the reflections. So if we have this case, the first thing I would realize is the first reflection, this reflection right here, is going to be an inverted reflection because we're going from a fast material into a slow material. So the reflection off that front surface ends up flipping phase by 180 degrees and being inverted. Some of that light, though, goes through the material, right? And then that light, some of it bounces off the back surface. Some of that light is going to be reflected. This reflection right here is not inverted because we were going from a slow material into a fast material. So we have an upright reflection from the back surface. The transmitted waves, or this transmitted wave right here, is not going to be inverted because transmitted waves are never inverted. So if I compare this wave with this wave right there, one of those waves was flipped. This wave was flipped, and this wave is not flipped. Okay. So the second thing to consider is that the wave that went through the second material had to travel further, right? So wave number 2 has a longer distance to go. It goes roughly twice as far, or twice the thickness of the film further than wave number 1, right? So if this is the thickness of the film, L, it's not perfect. There's some geometry there, but we don't usually consider the angles. Usually we approximate it by saying wave 2 has traveled a distance of 2L greater than wave 1. So under what conditions would we end up with constructive interference? Well, the very first constructive interference we would get is if L is equal to 1/4 of a wavelength, because in that case, 2L equals a half a wavelength, okay? And we're going to add the half a wavelength phase shift that is the difference between one of those being inverted and the other not being inverted, and we end up with a 1 wavelength difference between that first wave and the second wave. And 1 wavelength puts me back in phase, so we get constructive interference. We get another constructive interference if that film is thicker. So if the film is 3/4 of a wavelength thick instead, we would get a constructive interference again because we have then, doubling 3/4 makes 1.5, and then adding that additional half from the phase, from the reflection inversion gives you 2 wavelength difference, and 5/4 would give you 3 wavelength difference. So those are all of the conditions in which you would get constructive interference if this is your setup. Destructive interference, on the other hand, happens when my net or total, difference taking into account these two factors is going to be a half a wavelength, or some multiple of a half a wavelength. So if L is half a wavelength, then 2L is equal to 1 wavelength. And then when you add the half a wavelength for the inversion, you end up with 180 degrees phase shift, essentially, or destructive interference. And then we would get destructive interference again when the thickness of the material is 1 wavelength, because then we have, double the thickness is 2 lambda plus another half gives me destructive interference as well. If I lost you somewhere in that math, you're not alone. Understanding the nuances, I think, is a valuable exercise. However, if it comes down to it, memorizing this little bit will likely get you the credit that you need on a multiple choice question. I don't usually see this in an FRQ. The FRQ would expect you to really understand the reasoning why, but in any case, just having those sort of intervals memorized or written down would be pretty helpful for an MCQ question. So let's run through a quick practice problem. This is more like an FRQ practice problem. Assuming you have a bubble made primarily of water with air on either side of the film. So that's the same scenario that we had in the last slide. The film thickness is 500 nanometers, and the index of refraction of water is 1.33. I've got a few questions for you. The first is to calculate the speed of light in water. So go ahead and pause and do that. Okay. To do that, you would just use your n equals c over v equation, where n is 1.33, and you would end up with the result of the velocity of light in water is 2.26 times 10 to the 8th meters every second. Next question, calculate one wavelength of light that would have constructive interference and one that would have destructive interference. Probably the first wavelengths that would have constructive, and by first I mean the wavelength that would have, the first order constructive and the first order destructive interference. So the half wavelength and the quarter wavelength. So pause it for a sec. When you do the math, we realize that the first constructive interference appears where the length of the film is equal to a quarter of the wavelength. So my film is 500 nanometers. So that means if I multiply that by 4, the first constructive appearance would appear for 2,000 nanometer light. And the first destructive interference, where L is equal to half of a wavelength, would happen for 1,000 nanometer light. And then the last question is, what is this frequency and what would the wavelengths of these light waves be in air? So go ahead and pause and see if you can get those solutions as well. I would have used the wave equation to find the wavelength of those things, the frequency of those things in water, using the velocity I found above, because that's the speed in water, and the wavelengths that I just calculated. You can calculate what are the frequency of those waves. Then, if you want to know what the frequency and wavelength in air is, this is when you have to understand the science of frequency doesn't change when we go across a boundary. Wavelength does. So the frequency is going to be exactly the same as you calculated using the last wave equation, but we're going to now use the wave equation again, but change our velocity to c. And now we can use this wave equation in reverse to find what the two wavelengths are. And I got in air that first wavelength is 2,654 nanometers, and the other one is 1,327 nanometers. If you got through this, pat yourself on the back. Good work. So just for fun, why are bubbles in slope films colored the way they are colored, right? Why do we get this thin film interference that actually makes a rainbow of colors? Well, remember that white light contains all the colors and wavelengths. So for a given thin film thickness, some of that, one of those wavelengths or colors is going to be experiencing destructive interference, and others are going to be experiencing constructive. But actually what creates these patterns is more about the destructive interference. Because if you look at a rainbow minus a color, especially if that color is one of the colors that your eye cones detect, then your brain invents a color out of what's left. So you don't actually see the rainbow. You don't see Roy G. Biv in these bubbles very often. What you actually see is the reverse rainbow, the rainbow of the secondary light colors, or the colors that are created by our brain by seeing exactly two pigments and one of the pigments being destroyed. So the colors that you see, cyan, which is this beautiful teal blue that you see in a bubble, the magenta, which is obviously a really prominent color, and then yellow are what happens when two of the three primaries exist and the third one has been destructively interfered. So we see yellow in this oil slick when the blue light has been completely destroyed, and the only lights that are, you know, remaining are going to be the red and the green. Our brain invents yellow out of this. So the constructive interference effect is not nearly as strong because making one of the colors a little bit brighter will tint something, but you're gonna, as long as you're seeing all three colors, your brain tends to kind of normalize that out. So this is why we see an inverted rainbow and not a true rainbow in thin films. One more neat image that I wanted to just talk about and analyze a little bit here is this bubble film with a black background behind it. And so when you're looking at this, you see this cyan, magenta, yellow rainbow repeating over and over and over. And the reason you see that is because the film actually gets thicker, right? The film doesn't stay a constant thickness. It gets thicker due to gravity pulling on it. If you looked at a cross section of the film, it would sort of look like that as gravity pulls the water down to the bottom. So what we see is, like, at certain thickness, we see that first order destructive interference of one color, and then the film changes and gets thicker, and we see the second order interference of that. And so this is why we see a repeating rainbow. The top of that film, incidentally, is black because it is so thin up there that none of the colors in the visible light spectrum experience destructive interference, right? Where the path length difference isn't enough to end up with any, you know, any half or full integer value of that of the constructive or destructive interference. So we don't see any colors at the top because all the light is not, you know, we're not interfering any visible colors of light, which is kind of neat. All right, that's it for this video. Hopefully you guys now understand not just the rainbows that we see in the sky, but also rainbows that you sometimes see in bubbles and in other thin film phenomena.